Okay, so now that we've finished up writing some more word equations with your ions and your polyatomic ions, balancing them, writing the word equation, anybody have questions about those? You feel pretty confident in that now? How many of you feel confident in your polyatomic ions? Like if I were to give you a quiz tomorrow with every one of them, I don't remember how many there are, you feel like you would know 95% of them. Okay. All right, that's where you should be at this point. Let's look down this list of student learning objectives or I can statements really quickly and see where we are. You should be able to do number 1 at this point successfully. And number 2, we've been working on that. Write a balanced chemical reaction, give the proper information, yes. Predict products, we've been doing that. Algebraic examples and name the 5 types and pick them out. We've done that in lab and in class. Word equations, we just practiced that again. Prove that the reaction obeys the law of conservation of mass. We did not pull out our copper today and our zinc sulfate to weigh our copper, did we? So we will do that. It's not going to hurt for it to sit in the filter for a little bit longer. And what we're going to work on today, we've done a little bit with the calculating the formula weight, molecular weight, empirical formula weight. All of those things you should be comfortable with. The interconversions within stoichiometry you should be comfortable with. Calculate the empirical formula given the proper analytical information. We're going to get through that today. And so that's where we're going to start, and we'll see how far we get. I'm going to start with what I think is the simplest type of reaction to deal with. That's the way I have this typed up. And then we'll work into the more complex one. First of all, let's look at these words. Oh yeah, I'm sorry. I can see it, so I always think you can. I forgot I turned it off. I usually forget to turn it off. Today I forgot to turn it on. So we'll wait. Because it's low. So when I say empirical formula, Jackson, can you tell me what it is? Okay. So this should be popping up, yeah. The simplest or most reduced formula of a molecular compound. I want you to think about this for a minute. What type of chemical formula is always an empirical formula? Can you come up with an answer for that? What type of chemical formula of the ones we've been making and learning is always an empirical formula? What do you think, Kara? Synthesis, perhaps. I'm looking for one of the 2 big types that we've talked about. We've learned prefixes for what type of compounds? Covalent. And we've learned all of our polyatomic stuff for what kind of compounds? Ionic. Between covalent and ionic, which one's always an empirical formula? What? Good. Ionic. Why? Who said ionic besides Kira? Somebody else said it. Did you say it, Luke? Maybe. He doesn't want to answer this question. Why is an ionic compound always an empirical formula? What's the goal of an ionic compound? Yeah, to be neutral. So when I'm neutral, I should be in empirical form if I'm an ionic compound. Today, though, we're going to focus on some carbon and hydrogen containing compounds, which in that case, we have a molecular formula, so we have to reduce it to an empirical formula. So we're going to start with just the empirical formula analysis, and then we'll move our way through combustion reactions. So the first example I gave you on your handout on this yellow one was determine the empirical formula of a compound containing 0.013 mole of carbon, oxygen, and 0.039 moles of hydrogen, and then I gave you the oxygen. So let's look at what we have. We have carbon, we have a hydrogen, and we have oxygen. And what information were you given in the problem? You were given the number of moles, so we know the number of moles for each. So let's go ahead and list that underneath them. So I have 0.0130 mole. Here I have 0.039 mole. And here I had 0.0065 mole. So I'm given some very nice information. Like this, when you're given moles in the formula or in the problem, it gets rid of a couple of steps for you. So when I'm given all moles, the first thing I want to do is find the mole ratio. And I do that by dividing all by the smallest number. So my smallest number obviously is down here, so I'm going to divide each one through I know I'm going to get a 1 here. Let's go through. Go ahead and get your calculators out and figure out what you get for the other two. So this is a 1, a 1-to-1 ratio. When you have a mole ratio, or when you have the number of moles of hydrogen and carbon, stand up. Yours is bad as me. Mine always die. Here's one you can use.
Thank you.
So we'll wait just a second as we're had a calculator issue. Okay, Simon, how many moles of carbon did you get? 2. Anybody not agree with that? Brooke, how many moles of hydrogen did you get? She got 6 moles of hydrogen. Anybody not agree with that? So my mole ratio is 2 to 6 to 1. Make sense? All I do with that mole ratio is apply it to find my formula. So I would say C2H6O equals my empirical formula. That's about as easy as it can be. Now let's look at the back of that page, the example that we have. Determine the empirical formula of a compound that contains 11.66 grams of iron and 5.01 grams of oxygen. So the first thing I'm going to have to do, step 1 in problem number 2, would be go from grams to moles. So I want you to do that, and I want to see your work for iron and oxygen. We've already gone over this. You should know how to get to number of moles. Anybody have a question about how to set that up? Okay, try it. When you have your moles, stand up. When you have your moles of each, stand up. Okay. Anybody have any trouble setting those up? Seneca, what'd you get for moles of iron? 0.20 what? Anybody get anything different? Okay, and Kira Cole, what'd you get for moles of oxygen? Can you say that again? 0.313 is what I have, and I would say this is moles Fe, and this is mole O. Okay, so now, what I'm going to do with that, step 2, would be to find my mole ratio. So I need to do that. And I'm going to take, again, my largest number of moles divided by my smallest number of moles. So I always like to see what elements you're working with. We've got Fe and we've got O. Fe was 0.209 and O was 0.313. So I'm going to divide through by 0.209. And that's what I get. Did you get that? A ratio of 1 to 1.5. Can I use 1.5? No. So what do you think I have to do to that? What? Multiply by 2. Anytime you get one of these, you're going to multiply by what you need to get it to be a whole number. So I have to take this times 2. Whatever I do to one, I have to do to the other. So I have to take this times 2. So that gives me a 2 here and a 3 here. So my mole ratio is 2 to 3. So when I write that, Caitlin, how am I going to write that? Is this what you said, Fe2O3? Is she right? Okay, so let's double check this. Is she right? What's the charge on, how would I say this? Who knows how to say this formula? What kind of formula is it, ionic or covalent? What do you think, Haley? How'd you figure that out? Yeah, metal, non-metal. This is ionic. Evan, how would I say that? Evan. Iron, that's a good start. Iron, oxide. What am I missing when he says that? That's right, but we're just missing something. What's that, Kira? Iron 3 oxide. Kira, tell us how you figured that out. So when I look at this, O, what's my charge on O? It's 2 minus, right? And I have 3 of them. So that tells me this is a 6 minus. I have 2 iron, so I would divide by 2, which tells me that has to be a 3 plus charge. So I would say iron 3 oxide. Is that its most reduced formula? Yep. And it's an ionic compound, so it worked out perfectly. All right, let's go on to the next one, which says, determine the empirical formula of a compound composed of 40% carbon, 6.7% hydrogen, and 53.3% oxygen. So we're given a problem that contains percents, and we want to know the empirical formula. And I've got 40% carbon, 6.7% hydrogen, and 53.3% oxygen. When you are given these, the first thing you need to do is check and make sure they equal 100%. Does that equal 100%? Yes, so I know I've got everything. If it equals 100%, I can substitute and use that as 100 grams to represent my molar masses. So then the first thing I want to do is go from grams to moles for each. So this just becomes 40.0 grams, this becomes 6.7 grams, and this becomes 53.3 grams. So go ahead and do your number of moles of each. Set them up so they're clear. Carbon, hydrogen, and oxygen. When you have your moles of each, go ahead and stand up. Carly, how many moles do you have of, what would I do, carbon? 3.33 mole carbon. Haley, how many of hydrogen? 6.7 mole hydrogen. And Jackson, how many mole of oxygen? 3 point what? I didn't hear you, I'm sorry. 3.33 mole, is that what you said? Or did you say 2? 3.32? Oh, okay. Evan, did you have enough time?
Yeah, I have
3.23?
3.3.
Oh my lord, I can't hear today. Okay, 3.33, what I had written to begin with. Okay, so what's my mole ratio? I'm going to divide through by what, Caitlin? 3.33, okay. Well, this should work out pretty well. So this is a 1, this is a 1. And what's hydrogen? Is it close enough to call it a 2? It is close enough to call it a 2. So then I can just write my formula. It's a pretty simple one, CH2O. Okay, so example 4 approaches it from a different way. It says a hydrocarbon has an empirical formula of C3H4 and an experimentally determined molecular weight of 121 AMU. What's the molecular formula of the compound? So this is my molecular weight, or I could also call this my molar mass. And I want to know, what's my molecular formula? This is my empirical formula. Now think about that. Anybody have an idea of how we can use all that information and figure it out? What could I do? You think my empirical formula needs to be used somehow? Yes, it does. So what can I do? Let's find the empirical formula weight. Do that. That would be carbon 3 times 12 grams, and hydrogen would be 4 times 1 gram. So when I do that, think about that really quickly, that should equal 36 plus 4, that should equal 40 grams. Is that right? These are the easiest ones. What am I going to do now? I'm going to take my molecular weight and I'm going to divide it by my formula weight. So I had 121 divided by 40, which should give me about what? Pretty darn close to 3. So what do I have to do with this 3, do you think? What'd you say, Kira? Put it out front, sort of put it out front and do what with it? Multiply with it. So I have to take this whole thing times 3. So I end up with C9H12. Okay, go to example type 5. And I want you to move to your lab station with your lab partner only, so separate yourselves. And I want you to work through it. When you have an answer, come back and we'll compare. We've done one like it already. See if you can work your way through it. Check with each other each step of the way just to make sure you're on track. If you don't agree, call me over and we'll see where you've gone astray. When you have a final molecular formula, call me over and I'll check it. And the end of the problem, you should be able to give me the empirical formula and the molecular formula for your hydrocarbon. When you're ready, come see me as a group. Anybody having trouble?
Are we right or are we
You are
wrong?
right. Good job.
Yes.
Caitlin, did you get that too?
Yes.
Awesome. Good job. Yay. Very good. Good job. Brooke, did you get it? Okay, good job. Yay, people, yay! Come back, I'll teach you something harder. I've got one group to check yet. Yeah, we have one more. I need to see your formulas. Simon, and who's your partner? Yay! Good job. Very good. Are you with them? Okay, good job. Oop. Perfect. Thank you. Okay, so it looks like everybody didn't have any trouble with that. Let's do one that's a little more complex. Let's do this last one, which is the combustion reaction. Tell me what you know already about combustion reactions. Seneca, can you tell me one thing? Okay, my products, she said, are CO2. Did you say anything else? Good. Who can tell me what my reactants are? What do I always have to start with to get these things? Kira? Yep, some type of hydrocarbon and O2, very good. So I know, that's what I know so far. So I'm going to use what I know with this problem. Isopropyl alcohol is composed of carbon, oxygen, and hydrogen. I have a 0.255 gram sample, and it produces 0.561 grams of CO2 and 0.306 grams of H2O. And I'm being asked for the empirical formula. Okay, so I need to start these by taking my mass of CO2, and I want to get to moles of CO2. So let's do that first. My mass was 0.561 grams of CO2. If I have 1 mole of CO2, I have 44 grams, right? Because that's 16 times 2, which is 32, plus 12 gives me 44 grams per mole. So go ahead and punch that in and see how many moles we get. Oh, my calculator's dying. Carly, when you have a number, tell me what it is. 0.01 what? 8? 128. Okay. Mole. Ugh. CO2. So now what I want to do with that is I want to go from moles of CO2 to moles C. So I'm going to have to use a mole ratio. So I have my moles of CO2 being 0.0128 mole CO2. And I can use my mole ratio for every 1 mole of CO2. I put it on the bottom because that's what I need to cancel out. In every 1 mole of carbon dioxide, how many moles of carbon are present, Caitlin? How many? That's how many grams, how many moles? Is there any subscript behind this? Nope, so I would say 1 mole of C. In every 1 mole of carbon dioxide, there's 1 mole of carbon, and there's 2 moles of oxygen. I just read my subscripts. So I have 0.0128 mole of C. I'm going to box that off because I know we're going to have to use it later, and we want to be able to go back and find it. So then let's take our moles of C to grams of carbon, which I really could have done this in one big step, but I wanted you to see it broken down. So I'm going to go 0.0128 mole of carbon. Now I'm going to use Caitlin's other information she gave me. In every 1 mole of carbon, there are 12 grams of carbon. So I have to take that and do my math. When I do that, I get this little number, 0.1536 grams carbon. And again, I'm going to box that off because I need it later. I want to be able to go back and find them. Okay, so we just did that using carbon dioxide to find our carbon. Now we're going to use our water. So work with your carbon dioxide. Now we're going to work with our water. And we're going to go mass of H2O to moles of H2O. That would be step 1. Do that. When you have a number of moles of H2O, stand up. I'm going to run out of time. Shoot. When you have a number of moles, stand up. Luke, how many moles of H2O do we have? 0.017 mole H2O. Everybody agree with that? Anybody need to see it? Okay, so go ahead and box that off. And really quickly, well, no, let's set the next one up. Let's go moles. See if you can set this up. Moles H2O to moles H, not H2, moles H. See if you set that up right. And then check up here. Check your setup with mine. See what I did? 1 mole of H2O actually has 2 moles of H in it. And then figure out what that equals. Caitlin, did you get an answer already? 0.034. Anybody else get that? Okay, that's good. That's correct. Now let's take our moles of H and go to grams of H. Since hydrogen has a molar mass of 1 gram per mole, it should be the same thing. 0.034 grams of H. Box that off as well. And then we're going to use all those, the bell's about to ring, so we'll use, isn't it? What time do we get out? Yeah. So we'll use all these numbers tomorrow, and I'll show you how to put them together, and then I'll give you one to try on your own. And we'll move on. Any questions before we wrap it up? All right, have a great day.